Sounds funny.
All right, so if you look at that equation, distance equals 1/2 AT squared plus V naught time, okay? All this is for those of you that I'm guessing have studied functions in mathematics, this is just a function equation. So you can plug in, that's the initial vertical velocity, not your launch velocity, not the horizontal velocity. This is your initial vertical launch velocity. This is your time. That has to be a negative 9.8 meters per second squared. So this allows you to, this is one way to find the height at any point. Now, so if you're looking on that lab, here's where you can't do that particular equation. So if you look at that last question on the lab, so with that one we're saying here's this wall, which is 7.5 meters tall, which is pretty tall. I mean, this ceiling's like 2.5, okay? So you're up there a ways, right? So you're told when it's crossing that threshold that that ball has a speed, okay? Speed is just the number, of 36 meters per second at an angle of 28 degrees. So the first thing you need to do is break that into Vy and Vx, okay? So knowing that, and here's the leap of faith that you have to take. You need to figure out that velocity when it lands here. Because if you know the velocity that it has when it lands there, you know the velocity that it took off with, okay? Because we're assuming this thing is symmetrical. So here's the deal. You can't use the distance equals 1/2 AT squared plus V naught time because you don't know the time. Okay, so that won't, you can't do that because you don't have enough information, okay? But what you can do, because you don't know time, is that you can use that equation, okay? All right, that's cool. Now, here's the thing. You all are used to setting the initial velocity to be 0 because you're falling from the maximum height, okay? Like a lemming problem. But we're not. In this situation, it's like we're throwing, whoa, hello. It's like we're throwing the ball down, okay? So it's going to have some initial velocity, which is that Vy component. Now, and Kelsey, to her credit, realized she did something wrong. Because when she did this and she used that equation, she got a velocity here that was less than what it was up there. Okay? Because if you think about it, oh, it's already moving. It's going to be accelerating. And that acceleration is going to be making it speed up, right? And so this velocity here has to be bigger than what it was here. So what you have to watch is that when you're using that equation, and you've got that initial, what's that initial vertical component? 16.9 meters per second squared. And if you're going to use negative 9.8 meters per second squared, then you've got to use that negative 7.5 meters. You've got to make that distance a negative value, okay? So that way you, in effect, end up adding this part of it, okay? Because if you make that negative and you make that positive, then you subtract that part of it, and then you get an answer less than the 16.9, okay? So that's why you either make both of these negative or you make both of them positive, okay? It doesn't matter, they just have to be the same sign, okay? So then you can work backwards, go, oh, here's that Vx, here's that Vy at your launch, and then you can find the hypotenuse in that angle. So if all goes well, both your launch velocity and the angles should be in the 30s. Okay? So both of those should be in the 30s on that one. And make sure, like on the lab portion up above, you have shown your work, because everybody's data is going to be different. Okay, any questions on the lab portion? Yes, Kelsey?
So when you calculate the Vy, you're...
Which Vy?
So, okay, so when you do the one like Vy equals sine 28 times 36,
Yes.
that's calculating Vy initial, is that right?
Well, yes. In effect, in terms of looking at the analysis as it falls from here to here, yeah. in that regard, we are going to call that the initial velocity.
Okay.
And you're trying to find the final velocity when it lands.
Okay, so you use the one you calculated with sine to find.
Yes.
Yeah, okay. I just needed a label, what was initial.
Yeah, because that's how fast it's going at the beginning, and you're trying to figure out how fast it's going down here after it's fallen in another 7.5 meters.
Gotcha.
Okay? Cool with that?
Yes.
Okay. Now, on the other assignment, does anybody have any specific ones you want me to go over?
Yeah.
Now, well, let's talk about number 6. I want to make sure everybody's cool with number 6. So, let's make sure, actually, let's back up to number 3, because if number 3 is wrong, everything's going to be a train wreck. So, your total time on number 3 should be 6 seconds. Okay? And your range should be around 226 meters. So on number 3, your total time is 6 seconds, your range is 226. Now, that's going to be important, okay? So, that's if it goes from ground to ground. You got 3 seconds going up, and you got 3 seconds coming back down. If it's symmetrical, okay, and that's a huge if it's symmetrical. And that maximum height should be like around 44 meters. And again, that's pretty high up there. If you consider this ceiling's 2.5, 44 meters, those up there ones. So, when you get to number 5, what you want to do on number 5 is that here's this wall, okay, and you're 220 meters away, okay, which right away, if I'm going to try and clear this wall, if my total maximum range is 226, I know when I fire the paintball, if I'm going to clear this wall, I've got to be inside of 226, because 226, if I was 226 meters away, it would land at the base of the wall. So I know I've got to be in some if I'm going to clear this wall. So on that one, you know how far you're going to go, 220 meters. So you got a range of 220 meters, you know your Vx, find your time, plug that into distance equals 1/2 AT squared plus V naught time. So take 220 divided by your Vx, get a time, which is obviously going to be less than 6 seconds, because 6 seconds is your entire time. And then plug that in, and you should get an answer for this height of around 4.5 meters. Okay? So if you're 220 meters away, you fire that paintball. When it crosses that 220 mark, you're about 4.5 meters above. Okay, so you're going to clear the wall with plenty of space. So now what we want to look at in number 6 is say, okay, if we're 220 meters away, we're up above the wall. So what I want to know is, if I scooch this back, I just want to clear the wall. Now, so I know my answer to number 6, and this is what you want to think through. If at 220, you're well above the wall. At 226, you'd land at the base of the wall. So you know your answer to number 6 has to be somewhere between 220 and 226. Okay? So that at least gives you some kind of space. This is, oh, okay, here's what we've got. Now, there's 2 ways you can work this problem depending upon how you want to do the math. So one option is that you realize, oh, I got 3 seconds going up, okay, because I said I want to calculate this on the way down. So I got 3 seconds going up. At that point, you know your maximum height is about 44 meters, okay? Now, so you can use that handy-dandy equation that says 2D over G, okay? Y'all have used this before, okay? 2D over G, nothing like with lemming problems, right? Y'all have used this. But don't plug in the maximum height. Live long and prosper. I'll email you this lecture.
All right.
So, you don't use the 44, because if you use the 44, you're just going to get 3 seconds again. Okay? We don't want it to fall all the way down to the ground. we want it to clear that wall. So what you need to do for this is put in the difference between your maximum height and the top of the wall. Okay? So take your maximum height, subtract the 2.4, put that in there, find that time down, add that to the time up, and then use R equals Vx time. So that's one way you can do the problem. Okay? That's one way. Now, if you're a math nerd, here's your other option. Is that you can use distance equals 1/2, negative 9.8 meters per second squared, times t squared, and what's that initial vertical velocity?
37 point, or no,
29.4.
29.4.
So, if you're a math nerd, you can work this as a quadratic.
Which is 44.1.
So, if you're a math nerd, work it as a quadratic. So, you want your distance to be 2.4, okay? So there's your d. So then, to do the quadratic, you have to get one side equal to 0. And then you can set it up. There's your, A, B, C values. Plug that into the quadratic. Now, out of this, you're going to get two possible roots. What do the two possible roots physically mean when you get those two values of time?
Like the sides of the parabola one.
Yeah, which side? So you're going to get one time that's on the way up when it's 2.4 meters. And then your bigger time is when it's going to be on the way down. So that's why you can get two possible roots, because at two different times it's going to be at that height. So if you like quadratics, you can work it as a quadratic. And I think your calculators now, well, some of them, like, you just have to plug in the values and then it will do it for you, or do you still have to go old school, like b squared minus 4ac all over 2a? Okay. Anyway, I don't care how you do it. But your answer to number 6 should be somewhere between 220 and 226 meters. Your answer to number 1 should be around 13. Your answer to number 2 should be less than 1. We're good? Going once, going twice. Now, when you hand this in, do not staple them together. These are two completely separate things, okay? Do not staple them together. Keep them completely separate. We're good? Going once, going twice, sold? Okay. Brian, shut that down, please. All right, so here's the next big thing. Centripetal motion and gravity. So, let's start with something simple. So I'm going to take this rubber stopper and I'm going to spin it around over my head like this, okay? Now, once I get it up to speed, okay, once it's moving like this, constant speed, here's the question. Is the rubber stopper accelerating? Phil, you shake your head no. Why is it? Why do you think it's not accelerating? Huh? It doesn't look like it is, right? It isn't like I'm making it go faster, or it just kind of got this steady speed, okay? So you can make the argument that it's not accelerating because it's kind of going around at a constant speed like this. So if Fu is right, we're not accelerating, okay? Anybody think it is accelerating? Why do you think it's accelerating?
Because isn't it like, is it slowly moving like down or something? Like
What'd you say?
Direction? Is it changing direction?
Oh, let's talk about direction. So, here's the deal. Velocity is a vector quantity, too, right? So any vector quantity has two things. What does it have? Magnitude and direction. Okay, so let's see how we can study acceleration. So, Ryan, unplug that camera and let's bring it to the back of the room.
Okay.
Okay, so what this is called a liquid accelerometer. And no, that's not like blood from a freshman. Everybody asks that. It's like, that blood? No, it's just, it's a sophomores. Okay, no, it's just water with food coloring in it. So here's the deal. So I'm going to put this on here, and to the end of the string, I've got a 50-gram mass attached. Okay? And then I'm going to let go of it. So one of three things can happen to the water level inside here when I let go of it. I'm going to let go of it, and, well, the water has inertia, and it's not being accelerated, so it's just going to stay level. Okay, so that's option number one. I let go, the water stays level. Option number two, it's going to move in this direction, and that's the direction of the force, and the water is going to get pushed in that direction, so the water level would go up. Okay? Option number three is going to go in this way. The water wants to stay at rest, and it's going to go towards the back. Okay? So those are your three options. It's going to stay level, it's going to slope up towards the front, it's going to slope towards the back. So how many things the water level is just going to stay the same? Okay? How about slope forward? Slope back? Okay. Slope back. Okay? So why? Why is it going to slope back? Aiden.
Luke had his hand raised.
Huh?
Luke had his hand raised.
Because Luke has hand raised. Okay. All right, Luke.
Because it has its inertia and it doesn't want to move, so whenever the thing goes this way, the water stays back over there, so all the water gets pushed back that way.
Okay, no. Okay, you were good until you said one word. Okay?
What word?
You were good until you said the word pushed back. Okay? So first off, let's see what's going to happen, right? So I'm going to let go of it. All right?
You don't want to.
So we'll do it again. All right? So here's the question. Was it actually being pushed back, or did the water, because if it was pushed back, that would imply that there's a force in front of it pushing it towards the back. Okay? So that's the million-dollar question. Is there a force in front of it pushing it towards the back? Or does it just want to remain at rest and the back of the container is pushing it forward? There's a big difference between the
Second
two.
thing you said.
Huh?
The second one you said.
That it just wants to remain at rest. So imagine that I could do this. Imagine that the very instant that I let go of this, imagine if I could. If I could make the back portion of this container disappear as soon as I let go of it, what would the water do?
Leave.
Yeah. But would the water leave, or would the water just remain at rest? Yeah, it would just stay there, and everything would accelerate out from underneath it. Because the water has inertia, it has mass, it wants to remain at rest. So it slopes towards the back because of the fact that it doesn't want to move, and the cart's accelerating out from underneath it. So here's what's going to be important. The applied force is in this direction, right? The acceleration is in this direction, right? So the water level moves in the opposite direction of the acceleration. Okay? Now, if I take the 50 off, I will put on a 200. Okay? Now, if I put on a 200, now what's going to happen? It's going to accelerate faster. So what do you think is going to happen to the water level inside?
It's going to get higher.
Right? You'll see more of a change, right? So now when I do that, right? So, do that again. So we're here. Whoop. Pretty good acceleration.
Can you put the 1 kilogram
Hand me a 1 kilogram.
Oh.
I don't have one over here.
Jeez.
Can I catch her down there? Yeah, you need someone to catch her.
Hope the string doesn't break. Okay, you ready?
No. Sheesh, sorry.
Okay,
Immediately turned it on.
yeah, it just didn't have enough friction to hold it. Okay, so you got the idea. The acceleration is this direction, the water level went in the opposite direction. Okay, now, let's go back. Kelsey, I need you for demo for just a second.
Okay.
Ooh, Kelsey.
I got you.
Kelsey.
Yep. All you have to do is sit in the chair.
I can do that.
And do that. Okay, no, it's gotta go like this.
On it.
No?
Ryan.
Okay,
That's what I've
now-
been thinking this whole time.
I'm gonna take Kelsey and I'm gonna spin her around.
Oh, yeah.
Okay? Now, so again, there's three options that can happen when I begin to spin Kelsey. Option number one, if Foo is right, once I get her up to speed and it's not accelerating, what's the water level gonna do?
Just gonna stay.
It's gonna stay completely level, okay? All right, because Foo said, oh, it's not accelerating when I got it moving, okay? The other option is that we're gonna move like this, right? And the water level is going to be moving towards the inside. Option number three, the water level is going to be moving towards the outside, okay? So it can be level, inside, outside. So how many vote is going to remain level? One? Foo? Okay.
It's gonna stay.
How we can live with, I don't know. How about it's going to move towards the inside? Outside? Why outside? Zach?
Because on the diagram,
No.
those arrows going
Those
to the
arrows.
outside.
Okay, well, let's see what's going to happen. All right, are you ready?
Yeah.
Okay. Ooh. Now, as she slows down, what happens to the water level?
It got less steep.
Levels off, right? So the faster that she goes, you ready yet? Okay. So the faster that she goes, the steeper the angle is, right? And then as she slows down, it becomes flatter. Now, here's what's going to be important. So the water level went out this way. So what's the direction of the acceleration?
Inward.
Inward. Ooh. So when you're moving in a circle, the direction of your acceleration is inward. So if the acceleration is inward, which direction do you think the force is going to act? Inward, right? Because the force has to act in the same direction as the acceleration. Well done, dude.
Is that why like ice skaters like when they
That's angular momentum, which we will get to. Okay, that's angular momentum.
we're not there yet.
So here's the deal. So I'm going to take this rubber stopper, right? And I'm going to swing it around. So first off, is the rubber stopper accelerating?
Yes.
Yes. Okay? It's accelerating. So if you look at Newton's first law of motion, okay, which is the law of inertia, right? What that law says is basically it wants to maintain a constant velocity. In other words, it doesn't want to change anything. So, but remember, when you're talking about velocity, there's two components to velocity. There's the direction part, and then there's the magnitude part. Now, up to this point in time, until 10 after 8 on October 22nd, every acceleration problem that we've dealt with so far has been dealing with changing the magnitude. Okay, so I throw this up in the air. Oh, the magnitude of the velocity vector is changing. Okay, it's getting smaller on the way up, it's getting bigger on the way down. I push something. Okay, I'm going to change the magnitude. So all of our acceleration calculations so far have only dealt with the magnitude part of it. We haven't talked about changing the direction part of it. So when this thing is being swung around like this, okay, there's two parts to that velocity vector. There's the magnitude, and there's the direction. So once I get it up to speed, I'm not changing the magnitude of it, but what I'm changing is the direction. So if you look at this rubber stopper, and that's what Zach referenced, if you look at this rubber stopper as it goes around, okay, at any given instant, it has a certain velocity vector, okay, which has a certain magnitude and it has a certain direction. So if I spin this thing around, and this is where it goes back to this whole concept of the Jedi Stofa walk. You stop the force and you watch. So if I swing this thing around, right, and I let go of it, what's it going to do? Yeah, it's going to fly off in whatever direction. So by virtue of the fact that as soon as I let go of it, it begins to travel in a different path, that means that what I was doing was altering that path. So it's just like if I throw this rubber stopper up in the air and there was no gravity, what would the rubber stopper do?
Just keep going.
It would just keep going, right? So this is kind of the opposite of that mindset. So if I get that rubber stopper moving in a circle and I stop applying the force, it's going to take a different path, okay? So what's happening is that at any given instant, the rubber stopper wants to travel in a straight line. So what we're continuously doing is forcing it towards the inside. So this is why when Kelsey had this, right, and she was spinning around like this, what did that water want to do?
Go in the direction.
Water wanted to travel in a straight line, okay? Now, here's what's important, okay, and we'll talk about this in a couple of different situations. And this goes back to something that Luke said when we accelerated it that way. He goes, oh, it's like being pushed towards the back side. Here's what's important. When I do this, okay, I'm not, which would be cool, I'm not emanating a force which is pushing that liquid back. Because if I was, then it would going in that direction all the time. If I was emanating a force that was pushing it, it would do that all the time. But I'm not that cool. But so when I do that, okay, and again, visualize this. When I do this, the water just wants to move in a straight line. So imagine that I start to do this, and at the instant I start to do this, I remove this edge. What would the water do? It would just go off in a straight line, just like the rubber stopper does. Okay? So, when you talk about centripetal motion, okay, and we'll talk about that versus centrifugal in just a second. So centripetal motion centripetal comes from the Greek word meaning inward seeking. Okay? So centripetal means inward seeking. So what that means is that when you're talking about centripetal force, and we call that F sub c, and the C stands for centripetal, the centripetal force and the centripetal acceleration, AC, there's two parts to this. Number one, it always, without exception, none, zero, zip, only acts inward. Okay? It's not outward, it's not pushing it towards the outside, it acts inward. Now, the other part of this is that it is at a right angle to your velocity vector. So, at this point, if you look at this rubber stopper at this instant in time right here, if you could freeze frame it and go, okay, let's analyze that motion at this point. That rubber stopper wants to travel in a straight line. So, because we're forcing it towards the inside, that centripetal force vector, and then the acceleration vector that it causes, right, is going to be at a right angle to that velocity vector. So when I'm over here, the centripetal force is still acting inward, but it's acting like in a different direction from where it was over there. So now my centripetal force is acting in this direction, Now my centripetal acceleration is acting this way, but it's still at right angles to the velocity vector. So when I ask you this question, and I'm going to ask you this question a lot, okay? What's the direction of any centripetal force or any centripetal acceleration? Do not overthink it. There's no exceptions to this. You're going to go, oh, Mr. Burkamp, those act inwards and at a right angle to that velocity vector, okay? No exceptions, none, zero, zip. But here's the problem. It doesn't make any sense. What I just told you is completely counterintuitive to what we experience in life. And I'll show you why. You don't, great, Burkamp, we just talked about all of this and it's wrong. So imagine this, okay? So we'll stick with Kelsey, all right? So Kelsey graduates from high school, she's off to college, and she wants to be cool, and she's going to go buy a Jeep, okay? All right? And
I'm a Jeep girl, Volkswagen.
so here's Kelsey, right? And there's the part down the middle of her hair, right? Speaking of which, of hair, 1,000 bones, I'll dye my hair for those red, half green,
Bones?
$1,000 that will donate to the solar campaign. And if that money will count both ways, towards your class panel and towards your, so you need to hit up your older brother, because I'm guessing he might.
My brother's excited.
Wait, so that's combined classes?
You need to hit up your older sister.
I will.
So
She's broke right now, but
that's it.
Wait, is that combined classes or
She's
just
home
our
this
classes?
No, all, that, just $1,000 from everything.
Okay.
Yeah, that isn't just your
I was
class.
like,
take a picture of
No, that's like, so even if all three classes raise the money to buy the panel, you're about there.
yeah.
And somebody needs to hit up Dr. Botts, because I can guarantee you,
I got you.
he would hit
Do I
that
have
up.
permission to take your picture right now?
Huh?
Can I take a picture of you right now?
Why?
I want to put something on my story.
Okay,
Smile pretty.
I'm trying. That's as good as that was it. Okay, I'm in the zone.
I'm trying.
Okay. All right. So imagine, if you will, that Kelsey's driving, right? And she has like not split color hair, and she's driving in the Jeep, and she's going to take a hard right-hand turn. Okay, so she's driving. Imagine this one here is like, whoa, okay. And take a hard right turn. Now, what's Kelsey going to feel?
Going out.
Out, right? So she's going to feel like she's being pushed against that car door. Okay, that's what she's going to experience. Or if you've ever ridden like on a carnival ride where something spins. Okay, so you're on this carnival ride and this thing is like going around like this, and you're gonna go, oh, right. Okay, so Kelsey's gonna be like this, right? She's gonna be, oh man, I'm being pushed up against that. Or if you're one of my brother-in-laws, you're being pushed. Okay, man cannot say the word push. It's always pushed. Okay, so he would say, man, I was pushed up against the car. So if you're inside of this car, okay, you are going to have this experience like you're being forced up against the car door. You would say, oh man, this is what we call centrifugal force. Okay? So centrifugal force means outward seeking. But here's where this fails. Okay? Here's where this fails. So if centrifugal force is actually there, and you say, I'm being pushed or pushed up against the car door. Let's think this through. What would have to happen? Okay? So there would have to be some machine or something inside of your car that would emanate this force field that you can't see, okay, that you cannot see. And it isn't like we would see Kelsey's clothes get like indented, so it isn't like wind or something, right? So her clothes aren't going to be affected. So there's this magical field that pushes her up against the door, okay, but we can't see it. And this machine is clever because it's not going to act all the time. It isn't like, you know, Kelsey's going to be driving her Jeep in the straight line and all of a sudden, bam, she's going to get pushed up against the car door, okay? It's only going to be active when she turns. Okay? It's only active when she turns. And it's going to sense how fast she's turning. Because if she turns slow, it's just going to push on her a little bit, right? But if she turns really fast, it's going to push on her more. So this machine is clever. Okay? It only acts when she's turning, and it senses how fast she's going. And it emanates this field that we can't see. Seems logical. No, it's horrible. Now, imagine this. This won't happen because we like Kelsey. But imagine that Kelsey is in the Jeep, and we've taken out the door. Okay, we've taken out the door. We've taken out the seatbelt. No seatbelt. And it's a frictionless seat. Okay? Frictionless seat, no seatbelt, no door. Okay? Kelsey goes to make the turn. What's Kelsey going to do?
She's gonna die.
Now, is she going to fly out the door? Or is she just going to keep going in a straight line?
Keep going.
She's just going to keep going in a straight line. The car is going to accelerate out from underneath her. Right? So if you're up above, imagine that you're in a hot air balloon looking down. Okay? And you study Newtonian laws, and you all have. You would say, oh, if you're looking down on the top, you're just going to go, oh, Kelsey just wants to travel in a straight line because she has inertia. It's the car door that's forcing her to make that turn. But if you're Kelsey, and you're inside the Jeep, you are very much going to have this experience that I'm being pushed up against the car door. So within her frame of reference, oh, right, I'm being pushed up against the car door. But in reality, she just wants to move in a straight line. So what she feels is the action-reaction force of the car door. It's the same idea. Let's say Ryan is sitting here in this chair, right? And I come up from behind her and I push her. Okay? And she's going to do this, right? Now, when I do that, she's going to say, oh man, I was pushed back into the seat. But again, was there anything in front pushing her into the back of her seat?
No.
No. What's the only thing that happened? What did her body want to do? Stay at rest. So she feels the action-reaction force of the chair. So you being at rest and being pushed forward is the exact same phenomenon that's happening here. Okay? You just want to move in a straight line. You just feel that action-reaction force. Okay? Got that. Okay. So centrifugal is the Greek word meaning outward seeking. Okay? Centripetal, which is what we're going to study, means inward seeking. Okay? So that force is acting inwards at a right angle to the velocity vector. Beautiful. Okay. Now this is where we get a little bit poetic. 3 sources of centripetal forces. And by the way, if people want to donate through Venmo, we have a Venmo account for the Mays Solar Foundation, if they want to do Venmo. Okay. So, we have 3 sources of centripetal forces. What's one of them? Huh? Tension, right? So if I take this string, right, and I whirl it around like that, okay, there's a string. It could be a chain, something, okay? So tension is 1. What's another one?
Friction.
Friction. Now, this is the one that you're going to use most often, okay? So you get up, and you're going to make a turn, and you're going to walk towards the door. When you make that turn, you are undergoing centripetal acceleration. But when you make that turn, what does your body want to do?
Keep going.
Body wants to keep going towards the wall, right? Now, if there's no friction, guess what? You're not going to make the turn. You're just going to keep going in a straight line. So when you turn your car, right? So if you think about it, you have 3 ways now to accelerate your car. Okay? You're going, no we don't, just have the gas pedal. Okay? And it is. Gas pedal's one of them. So when you hit the gas pedal, in terms of velocity vectors, what's the function of your gas pedal? Make the velocity vectors get bigger. What's the function of the brake? Makes them get smaller. What's the function of the steering wheel? To change the direction of the velocity vectors. Okay? To change the direction of your velocity vectors. So every time you turn, you're accelerating because you're changing the direction of your car. Okay? Now, you can also, and I don't think people do it as much, but some people, it used to be the rage to like hang stuff from your rear view mirror. Okay? And some people would like, when you graduate, they'll take like their tassel and they'll hang it from the rear view mirror or something like that. Or the fuzzy foam dice, something like that. Okay? You know, or some people do like any number of things. So basically, when you're driving in a straight line at a constant speed, that thing's going to hang straight down. But imagine that if I'm here, and let's say here's my car and I'm facing this direction, and I hit the gas pedal, what's this thing going to do? Now, is there something forcing it to the back?
No.
No, it just wants to stay in place, right? Now, if I'm turning, okay, if I'm going to turn in this direction, what's it going to do? Yeah. So if you have something hanging from your rear view mirror, you can use this to indicate if you're accelerating. So if this thing is moving one way or the other, you're accelerating. But again, think this through. If I push down on the gas pedal, this thing is going to go back like this. So it's just like the liquid accelerometer. It's going to move in the opposite direction of the acceleration vectors. So if you're turning and you see that thing move, oh, you're accelerating. Oh, okay, right. Now, so the third one is gravity. And that's kind of important, okay? So if you look at the star, our nearest star, otherwise known as our sun, and here's this rock that we're on, okay? So is the Earth accelerating towards the sun? Yes, and that's a good thing, okay? So you can go home today and tell the parental units like, oh, we learned today in physics that we're falling towards the sun, okay? And people might flip out like, oh my God, we're gonna die, we're falling towards the sun. Okay, the alternative is we don't fall towards the sun. We move off in a straight line tangent to our orbit. We're going to get awfully cold and awfully dark really, really fast. Okay, so it's actually a very good thing that we're falling towards the sun because the alternative is really bad. Okay, now you all are on this spinning rock that we're on. So right now, are we all undergoing centripetal acceleration? Yeah, because as we go around, so here's Polly the penguin, right? So here's Polly the penguin. Polly the penguin at any point wants to do what? Polly the penguin wants to go off in a straight line, okay? But gravity is holding us to the spinning rock so that we don't go off in a straight line and we continue to travel in a circle. So let's say, hypothetically, let's look at a scenario. So here's Kelsey in her Jeep, and this is looking down on top. And here's the intersection of 21st and Mays Road. Okay, and she wants to take a hard right turn. Okay, so she's going to go Charlie's car wash. So she's going to make this turn. So typically, what's going to create the centripetal force that's going to allow her to make that turn? Friction is, right? Okay, she's going to turn the tire. There's the wheels. There's friction between the tire and the pavement. She's going to make this turn. Okay, so typically friction is what's going to allow that to happen. But let's say that we've had like a massive ice storm, and 21st is like a sheet of ice. Okay, sheet of ice. She can still turn her steering wheel, but what's going to happen? She's just going to keep going in a straight line because of inertia. It's like, oh man, but she's going, man, I really got to take this corner. What am I going to do? So she looks in the back seat. So if you've seen any of the Indiana Jones movies, okay, what does Indiana always have? Got his whip, right? His bullwhip, okay? So you happen to have one with you, and there's a telephone pole right there on the corner. Okay? So Kelsey's gonna go all Indiana Jones on us, right? She's gonna take that bullwhip, wrap it around the telephone pole.
Driving behind the scene.
What, yes, and go boom, right? So if we're gonna do this, we're gonna do this right, okay? So then she's gonna hold on to it, right?
Some grip strength.
Whoa, yeah. Mad strength. And then so she's gonna hold on to it, right? And it's gonna go around like this, and then when she gets to this point, what's she gonna do?
Let go of it.
Let go of it, and then she can continue on in a straight line. Okay? So that's an option. Okay? Now,
Break and go get the lunch
The-
and come back.
other option, and this would be even cooler. So she looks in the back seat, and she has a bottle of Acme dehydrated black holes. Okay? Deep gravitational source, right? Black hole. And all you have to do is add water. But they're dehydrated, right? So add water, boom, get a black hole. So, but they only last for like 3 seconds. So here's an option that she could do. She throws the dehydrated black hole out. She takes a squirt gun and she pours some water on it. And it instantaneously creates this very, very intense gravitational well or source. And so she would basically pulled into orbit around the black hole, right? But it only lasts for a short amount of time. So then, as soon as she makes the corner, she knows that that's going to disappear. The gravitational source is no longer there. She can travel on her own merry way. Okay? So that would be the coolest one. It's like, oh, you want to make a turn? Oh, we'll create a gravitational well right there in the corner, and then you can make the turn. Now, the other option is that she gets all of her physics cohorts to stand out here and like push her car as she's going around. Okay? So everybody's going to stand there and it's like, okay, when she gets, okay, push, push, push. So everybody would be like pushing her as she goes around. It's like, we got to get Kelsey to make this turn. This is important. So everybody's going to go make like this human wall and push her towards the inside as she's going. Okay? But here's the point. Without an external force, she's not going to make this turn. Because what's she going to do? She's going to go in a straight line. Okay? That's the basic idea. All right, so let's talk math. Okay. So the simplest way to calculate centripetal acceleration is velocity squared over r. Now, if you look on your equation sheet, so if you look on your equation sheet, down here, it's about halfway down, you're going to see a bunch of equations relating to centripetal force. So if you look at this centripetal acceleration equaling v squared over r. So if you look at the units, and to derive this, you've got to do some calculus because it has to do with like rate of change in your velocity, in the direction of your velocity vector. We won't go through all that. But if you look at v squared over r, what's that velocity going to be measured in? Meters per second, but that's going to get squared, so we get meters squared over second squared. And then we have a radius that's in meters. So the meters cancel out, we get
Acceleration.
meters per second squared, which is what acceleration is measured in. Okay? So you can look at it and go, oh, that has to work because that's how the units work. Okay? So that's the basic idea. So then centripetal force is mass times centripetal acceleration. Okay? So it's just F equals ma. So you can rewrite this as mv squared over r. Oh, okay, that's cool. Now, and oddly enough, if you look at the units, you're going to get kilograms meters per second squared, otherwise known as newtons. Okay, so now there's another way that you can look at this. So let's say that I'm going to take this rubber stopper, and this is where a lot of this stuff, no pun intended, goes full circle in terms of what we've studied so far. So if I'm going to move this thing around, okay, if you go back to the very first test that you all took, and we were calculating like the velocity of the Earth as it goes around the sun, okay, remember that problem? Okay. So, as this thing makes one revolution, how can I figure out how far it's going? How can I find the distance that that rubber stopper is going to travel?
And the radius of the.
If I know the radius, I can find the
circumference.
the circumference. And how do you calculate the circumference of a circle?
2 pi r.
2 pi r. Ah, right. So as this rubber stopper is going around, right, velocity is going to be 2 pi r, because that's going to be the distance that it's going to travel, right? That's all it is. Now, because we're making one complete loop, do we use lowercase t or uppercase t? Uppercase t, because that's period, right? So that's uppercase t. So all this is, oddly enough, is just distance divided by time. Okay, so 2 pi r over t is just a really fancy way of saying distance divided by time. So in the lab that you all are going to start on Monday, that's one of the things that you're going to do. You're going to measure how much time it takes for a rubber stopper to go and make one complete revolution, and then you're going to know the radius, and you're going to calculate the velocity from that. So here's where the hocus pocus happens. So we said that centripetal acceleration was v squared over r. Now this is the pirate's favorite thing, okay? Because what's the pirate's favorite letter? R, right? So I got v squared over r. So then I'm going to take, for v, I'm going to substitute in 2 pi r over t, but that's going to get squared, right? And then I'm going to divide that by r. So now when I square all this, I get 4 pi squared r squared over t squared divided by r. So this is where the pirate doesn't like this step. So what's going to happen to one of my r's? Oh, I'm going to lose one of my r's. So I got 4 pi squared r over t squared. Now, that's kind of cool. So look at the units. The radius is going to be measured in what? Meters. T is going to be in? Guess what? I'm going to get meters per second squared. Oh, how cool is that? Now, here's what you're going to screw up. Mark my words. This is what you're going to do wrong. And you all sit there and go, Mr. Burkamp, we won't do that. You lie.
I'll do that.
You're going to forget to square pi. Okay? That's because you all have never probably had to square pi in your mathematical calculations. Okay? So that's going to be a little bit out of your comfort zone. Okay? So don't forget to square pi. So at this point, here's what we have. So we have centripetal force equals mass times centripetal acceleration, which is also mass times v squared over r, which is also mass times 4 pi squared r over t squared. So which one you use just depends upon the information that you're given. Okay? So if you're given like, oh, hey, Zach is running in a circle, and he's running at 5 meters per second, and the radius of the circle is 5 meters, oh, how much force is that going to take? Just use v squared over r. Okay? Now, but if I tell you that Zach is running in a circle, and it takes him 5 seconds to complete the circle, and you know the radius, then just use r over t squared. Okay? Now, and this makes sense once you get into some of the problems. You don't have to calculate the velocity separately and then plug it into v squared over r. So if you're not given the velocity directly, just use this r over t squared. Okay? So you don't have to calculate the velocity separately and then use mv squared over r. Just use m 4 pi squared r over t squared. Okay? It's just going to make life simple. Okay. Now, so let's talk about the green spinny thing. Okay? And we're going to use the green spinny thing a lot. So I'm going to take this and So we got a couple of dimes, okay? So put a dime out there,
Any pocket.
okay? So make the dime go around like this. So is the dime accelerating?
Yes.
Yes. How do you know?
It's changing direction.
It's changing direction, right? Because what does the dime want to do?
Stay straight.
Either, right now it wants to stay at rest, right? But then when I get it moving, what does it want to do? It wants to go in a straight line, right? Okay. So when this thing is moving, okay, so here's the dime. So here's the dime. When that thing is moving in a circle, there's three forces acting on that dime. What are the three forces?
Gravity.
Gravity is one, okay? So that's kind of cool. Gravity is pulling it down. What else you got? What? Friction. Now, which direction is the friction going to have?
Inwards.
Inward. Okay? And then there's a third one. Huh? No, there's no strings. Rhymes with normal.
Normal force.
Oh, your normal force. Right? So, these two are the ones that, this is old school, right? Oh, it's sitting there, it's spinning. Gravity's pulling it down. It's being pushed back up. So, this frictional force, right? Because if there was no frictional force, what would it do? It wouldn't do, just move off in a straight line. So imagine I could get it spinning, and then I shut off friction, quarters out of it. So here's what's important. The frictional force is creating the centripetal force. So here's the anomaly about centripetal force. So if you look at the four fundamental forces, electromagnetic, gravity, nuclear, centripetal force isn't listed there, okay? Because here's the anomaly about centripetal force. So we're going to spend a lot of time talking about it, but centripetal force only exists because there's something else, because there's friction, because there's gravity, because there's a strain, okay? So centripetal force only exists because something else is present, okay? So this is why centripetal force isn't one of the four fundamental forces, because it exists solely because of some other thing happening, right? So when I move this thing around like this, right, okay, it's going to be undergoing centripetal acceleration. And that centripetal acceleration occurs because there's friction. Now, this is where, like I said, a lot of this is going to go old school. So we're going to look at the coefficient of friction being forced friction over force normal. Okay? Now, what we're assuming is that the centripetal force, which it is created by the frictional force. So we're going to substitute in centripetal force for force normal. Now, because we're on a flat surface, whoa, go away. Because we're on a flat surface, the normal force is equal to what? Gravitational force. Wow. So I could rewrite this as mass times my centripetal acceleration divided by mg. Okay? Now if you do this, you look at it from this perspective, what's going to happen to your mass? It's going to cancel out. So on a flat surface, when something's going around like this, here's what you have to understand. The frictional force is what's creating the centripetal force. Centripetal force is mass times your centripetal acceleration. Force normal is the same as your gravitational force, which is just mg. So mu, you can also look at mu as being a ratio of your centripetal acceleration to your gravitational acceleration. But again, remember, this is like an absolute value. Okay, so don't go, oh, g is negative. No, it's an absolute value. Okay? All right. Now we're going to spice it up a little bit. Put a second dime on here. Okay? So move this around like this. So here's the question. Which dime takes longer to go around? So imagine Taylor's timing the inner dime. Colby's timing the outer dime. which one's gonna have the longer time period? The inner, the outer, or are they just gonna be the same?
Same.
It'll be the same. So here's what's important. So when I look at this green spinny thing, okay, dime here, they're both going to have the same period because they're both going to take the same amount of time to go around. That's the same, right? Is the radius is the same?
No.
No. Which one is going to be going faster?
Yeah.
The outer dime. Why?
More expensive.
Yeah, it's got to travel a greater distance in the same amount of time because it has to go all the way around like this. So imagine that you're running, okay? You're on a track. Zach's on the inside, Aiden's on the outside, okay? Now, if they both start at the same point as they go around, who's going to win? Even if they're running at the same speed, who's going to win? Zach is. Why? Because Zach doesn't have as far to run. This is why if you've been to a track meet and they'll stagger the runners, because the one on the inside, right, has an advantage because the one on the inside doesn't have as far to run. So that's why they stagger the starts. Okay. So here's the question. I'm going to go around like this. Which dime is going to fly off first? The outer dime, the inner dime, or are they both going to fly off at the same time? How many vote outer? Okay. How many vote inner? How many vote the same? Okay. How many vote it's going to be the same time? Okay. So, what's keeping them moving in a circle?
Friction.
Friction. Is there a limit to what friction can do?
Yes.
Yes. So, look at this in terms of the centripetal force is going to be mass times 4 pi squared r over t squared. Okay? Right? Is the mass of each dime the same?
Yeah, probably.
Yes. Is the period of each one going to be the same? Yeah. So as the radius gets bigger, what happens to the amount of centripetal force that you need? It gets bigger, right? So the further out you are, moving with a constant value of t, the bigger the radius is, the greater the centripetal force, because you're moving faster, right? So I'm going to spin this up. Outside one flew off first, because there's a limit to what friction can do. And so as that went faster and faster and faster, that outside one exceeded that frictional limit first, because friction's going, I'm trying, like, oh, I can't do it. And it just says, ah, fuck, screw it, just go ahead and go. So, forget it, you're out, friction stopped, you're on your own. Now, imagine that we can do the same thing, and I've got this little rubber stopper, and I can swing this around, and I can do this pretty safely, right? Okay? Nothing's going to happen. But do you think I'd want to do that and swing Hank around? No. Why?
Because there's more of a chance to hit you.
Why? I'm not worried about it hitting me.
Because it's heavy.
I'm more worried about what?
It flying off. And
I'm more worried about it flying off because the string, right, isn't very, because I can just take the string and go boom and break it. So if I tried to swing Hank around, I'm going to exceed that limit pretty quickly. And once that limit gets exceeded, bad things are going to happen, and it's going to go off in a straight line tangent. Okay? It's like, what happened in class today? I don't know. I killed one of the students. Really? What happened? So, here's what I want you to see.
Hank killed a student.
Hank did it, I didn't.
Yeah.
Anyway, so here's what I want you to see. Quick summary. Centripetal force never exists on its own. It has to be created by something else. Tension, friction, gravity, something. Okay? The faster that you're moving, the more centripetal force that you need. Now, here's an interesting thing. Because centripetal force also equals mv squared over r, if I double the velocity, what's going to happen to the amount of centripetal force? It's going to quadruple. It's going to go up by a factor of 4. So if you're driving around over the weekend, hanging out with your friends, right, and you take a turn, and let's say you look down and you're going like 20 meters per, or excuse me, 20 miles per hour. And everybody goes, oh, that was cool. Let's go up to 40 miles per hour. Okay? And you're going to double your speed. Well, if you double your speed, your centripetal force is going to go up by a factor of 4. Okay? Probably not ought to do that. Now, here's the question. Can I move in a circle at constant speed? Can I move in a circle at constant speed? Yes. Imagine this. We're going to go out in the parking lot, okay? We're all going to hop in Ryan's car, okay?
You can fit.
We can fit.
Yeah.
Okay?
I'll sit in the truck.
And Ryan's going to get in and she's going to set her cruise control at 5 miles per hour, okay? So her speedometer is going to stay at 5 miles per hour. But we're going to be moving in the car, right? Going around like this, okay? So we're going to be traveling at a constant speed because that speedometer is going to stay at 5 miles per hour. So we're going to be traveling at a constant speed. But are we still accelerating?
Yes.
Yes, because we're moving at a constant speed, but we're changing our direction. Okay? Got that? Okay. All right, so stop that for a second. Okay, so here's the drill. So let me set this up. You've got, imagine a marching band, okay? And there's a line, and they all want to move like this. So imagine I'm going to line you all up, and we're going to travel around in a line. So you got Betty Joe. Here's a radius of 1 meter. Bobby Joe has a radius of 8 meters. And they're going to march around in a line like this. Now, notice that every bit of information that I've given you has 3 significant digits. Every answer on number 1, which is just the entire page, front page. So make sure that every answer that you give me has 3 significant digits. Okay? 3 significant digits. So, on the back side, so all this is just manifestation of the same thing. U equals force frictional, force normal, centripetal force, all this good stuff. Now, let me explain what's going to happen on number 6, because number 6 is where lemmings meet projectile motion, meet centripetal motion. Okay? So, what's happening on number 6 is this. So, a .02 kilogram ball, which looks like a rubber stopper at this point, I'm going to swing this thing over my head. Okay, so visualize this. I'm swinging this thing over my head. And it is 2 meters, or 1.8 meters above the ground. So let me kind of get you this visual. So here's this ball, and it's 1.8 meters above the ground. Okay? So I'm swinging it around like this, in a horizontal plane like this. Okay? Now, I'm going to let go of it. As soon as I let go of it, what is it? What type of problem is it? It's a lemming problem. Ah, it's a lemming problem. So you're told that it lands. So I'm going to let go of this thing, and it's going to go like this. And it's going to land 4.4 meters away from where I let go of it. So don't even worry about circular motion at this point. Do not even worry about circular motion. Go old school. Oh, it's a lemming problem. It's 1.8 meters tall. So what can you find out from the height? What if it was just 1.8 meters tall and I just drop it? What could you find?
Gravity.
Well, we know what gravity is.
Wait.
Okay. We can find time, right? We can figure out how long it's going to fall, right? Oh, old school. What's the lemming problem? We can find time. Knowing the range, what else could you find? Range equals
Horizontal.
Vx times
Time.
time. Oh, you can find your horizontal velocity, right? Oh, okay, right.
How do you know what the range is?
Huh?
How do you know what the range is?
Because I told you that it lands 4.4 meters away. That's how you know the range, okay? So you can find the time, know the range, you can find your Vx. Then it's like you're working backwards. Then you know how fast it was going when you let go of it. Then, once you find that Vx, then you can calculate,
Banjo.
ooh, that was bad. Centripetal force equals mv squared over r. So, find your velocity from the Lemming problem. I gave you the mass of the ball and the radius of the swing. So this is what you want to do. So on that last problem, do a Lemming first. So this is a quick way to review for the test. Do a Lemming problem, and then roll it into a centripetal force problem. Okay? Got it? Good? Grand? Let's call it a day.